Welcome back to my sessions on fundamentals of electrical engineering. We had finished a module on signals and systems. Most of the problems that were covered in GATE examinations for electrical engineering students were covered. And then we had moved on to control systems. In control systems, of course, it's a logical progression from signals and systems. And we had two sessions wherein some aspects associated with systems using the transfer functions were discussed. How to form the transfer function, both the closed loop transfer function, as also how to use them using the damping factor, the poles, the natural frequency. All these things were discussed. Okay, we also looked at the steady state error, both for step input as also for the ramp input. Mostly step input because there are three different ways of doing the same problem. Okay, most importantly, it is the final value theorem which is being used. In this session, in fact, we have a couple of sessions in time responses. They are mostly related to each other. And so let's go to the first problem. The first problem, we are given four response curves. Yes, it's y with respect to time. And then, the first one starts at -2. It's exponential, no doubt. Similarly, the second one starts at, B starts at +2. And it's again a decaying exponential. C is again a build up, but then it starts at -0.75. And B starts at +0.5 also. It's a decay again. A and C happen to be building up, while B and D talk about a decaying kind of exponentials. Okay, for the response. So, and what is asked is unit step response. Okay, unit step response. So the input is 1 by S. With the transfer function Gs is equal to 1 minus 2S by 1 plus S. Okay, so 1 minus 2S by 1 plus S can always be written as equal to 1 plus S by 1 plus S, which is equal to 1 minus 3S by 1 plus S. Okay, so when you multiply by 1 by S, the good thing is that you get 1 minus 3S by 1 plus S. Okay, and its Laplace inverse is very easily identified as ut minus 3 into e raised to minus t. Okay, 3 into e raised to minus t. Okay, so when you talk about and then which is given by the following. So at t equal to 0, 1 minus 3 into e raised to minus t is going to be -2. Okay, no doubt about it, because and that's all. Option A is going to be correct. That's all that we need to realize. That is, the curves are exponential; they are building up. Okay, of course, the Laplace transform tells us that they are building up curves. So A and C happen to be better, but at the same time, at t equal to 0, you get 1 minus 3 into e raised to minus t. So it's -2. Okay, at t equal to 0. Moving to the second problem, the transfer function of a linear time invariant system is given as Gs is equal to 1 by S square plus 3S plus 2. Okay, the steady state value of the output of the system for a unit impulse input. The unit impulse input applied at time instant t equal to 1 is the same as having a Laplace transform as equal to 1 into e raised to minus s. Okay, so the output is now going to be e raised to minus s divided by s square plus 3s plus 2. Okay, and the steady state value, for getting the steady state value, final value theorem, multiply by s and then put s is equal to 0. Okay, so that s stands independently there. E raised to minus s becomes 1 when s is equal to 0, and the denominator becomes 2. So when you set s is equal to 0, you get a response as equal to 0. Okay, so steady state value is output is equal to 0 just by virtue of the input being an impulse, which does not have a s in the denominator for cancellation. Okay, so moving on to the third problem, wherein we are shown omega square divided by s square plus 2 eta omega s plus omega square, getting a controller. Okay, it's a proportional cum integral controller, and the proportional cum integral controller will always see to it that, especially the integral controller will always see to it that there is no error, or the input is passed on to the output. Okay, so consider the feedback system shown below, which is subjected to unit step input. Okay, so if unit step input is going to be the input, then the output as also z, which is shown, is going to be equal to 1. Okay, the system is stable and has following parameters: kp is equal to 4, which does not matter, ki is equal to 10, omega is equal to 500, and eta is equal to 0.7. Steady state value of z. Okay, so z is at the output of the integrator, which is always going to integrate what is called as the input. So you're going to get what is called as you're going to get the output as equal to 1. Okay, so moving on to the next one, you have a unit impulse response of system is given as CT. Okay, so this is CT is the unit step response, unit impulse response. So CS can be the same as equal to HS. Okay, so minus 4 e raised to minus t, 6 into e raised to minus 2t. The step response of the same system. Okay, so if unit step response is given by CT as so much, then step response is going to be given by the integral of of CT or with respect to time. So now we have two terms. One is going to be the minus 4 into e raised to minus t. When you integrate, you get is equal to 4 into e raised to minus t. Okay, or minus 4 e raised to minus t divided by minus 4. So we have two terms with 4 e raised to minus t, that is B and C. Okay. Then we move on to the next term, that is 6 into e raised to minus 2t when integrated with respect to time gives you 6 by minus 2, that is minus 3. So B seems to be having both the terms appropriately with appropriate coefficients, minus 3 raised to minus 2t plus 4 raised to minus 3. And what about minus 1? That is coming as a result of the integration constant. Okay, so we have plus c there, and then at t equal to 0, we see that 1 is equal to, that is the input, is the same as equal to minus 4 plus 6 plus c. So c is equal to, c is going to be equal to minus 1. Okay, so 6 minus 4 is 2. 2 minus 1 is equal to 1. Okay, so very simply we have done this particular problem. Next one is we have a diagram of the response CT as t goes to infinity, starts at 0 and builds exponentially to a value equal to 2. The initial slope is shown as equal to, at t equal to 0 is shown as equal to 2 by 0.2 or is equal to 10. Okay, and RT is given and CT is obtained after a while passing through a block given by k by s plus a. Okay, and what is asked is the first order system and its response to a unit step input. Okay, so unit step response, the unit step input means that CS is the same as equal to 1 by s into k by s plus a, because RS is equal to 1 by s. Okay, and so so now we can find out CT as L inverse CS as equal to L inverse of 1 k. You have 1 by s into k by s plus a. Okay, so it's very simply, you can see that both the residues happen to be k by a, whereas for 1 or ut it's going to be plus, and for e raised to minus at, because our 1 by s plus a going on to e raised to minus at will have residue as given to minus k by a. Okay. So now CT is equal to k by a into 1 minus e raised to minus at. So there are two options. One is at t equal to infinity, where in the output stabilizes to 2. So 2 is the same as equal to, when t equal to infinity, e raised to minus at becomes 1. So 1 by, so it becomes equal to 0. So k by a. Okay. So k by a is equal to 2. And others, of course, when you take the differential at t equal to 0, when you are having a slope given by 2 by 0.2 or 10. So that's equal to dct by dt at t equal to 0. When you take the integral of k by a into 1 minus e raised to minus at t equal, it is the same as equal to k by a into minus a or k. Okay, into minus of k by a into minus a, which is equal to k. So k is equal to 2 by 0.2, which is equal to 10. Okay, so now k is equal to 10 and k by a is equal to 2. So very easily you can find out a as equal to 5 and k is already obtained as equal to 10. Moving to the sixth problem, for the system 2 by s plus 1. Okay, the approximate time taken. So 2 by s plus 1 tells us about 2 into e raised to minus t. Okay, so e raised to minus t is the way in which the system is going to the system is going to grow or decay. The approximate time taken for a step response to reach 98% of its final value, or in other words, 2% is left. 2% is left means 0.02 of the of the step. Okay, step input is of course any value, but of course we can take it as unity such that we can say that we now have e raised to minus 1t will now have to deliver what will be called as 0.02. Okay, so if you take the natural logarithm on both sides, it is going to be ln of 1 by 0.02. Okay, so that's the same as equal natural logarithm of 1 by 0.02 or ln of it's the same as equal to 50. So that will be given as equal to 3.91. So from amongst the four options, 4 seconds is nearest. So we go for that. Okay. Moving on to seventh problem. The function yt satisfies the following differential equation: dy by dt plus y is equal to d delta t. Okay, so Laplace transform will give you s plus 1 into is is equal to 1. Okay, so these things you can see immediately where delta t is the delta function, assuming zero initial condition and denoting the unit step function by ut. Okay, yt can be of the form. Okay, so what is yt? So just take the Laplace inverse of 1 by s plus 1, that gives you is, that's equal to e raised to minus t. Okay, of course it starts at t equal to 0, so you have to signify e raised to, you have to develop e raised to minus t further by multiplying by ut. Consider the eighth problem wherein the function fs is given as 5 by s into s square plus 3s plus 2, where fs is the Laplace transform of the function ft. The initial value of ft is equal to, so what's the initial value? You can find out using the initial value theorem by multiplying by s and putting s equal to infinity. Multiplication by s will cancel out the 2s, but the s square on the denominator, when it goes to infinity, will give you a value equal to 0. Okay. Otherwise also, now this the function fs will have two components. One will be 1 by s, the other will be something with a negative value. So they can cancel and you will have, okay, of course, s square plus 3s plus 2 is having two components. One is e raised to minus 2t, the other will be e raised to minus t, because it's the same as equal to s plus 2 into s plus 1. Okay, s square plus 3s plus 2 is the same as equal to s plus 2 into s plus 1. So there are three components. So it's obvious that they will cancel amongst themselves. Okay, and that's the reason why initial value theorem is working out to be okay. Okay. Moving on to the ninth problem. A control system is defined by the following mathematical relationships. Just have a good understanding of mathematical relationship, which has d square x by dt square, 6dx by dt plus 5x. So these are three terms on the left hand side. The right hand side you have 12 into or 12 minus 12 into e raised to minus 2t. The response of the system is t tends to infinity. What is special about this mathematical relationship is that any oscillations at t goes to infinity becomes 0. Okay, or in other words, d square x by dt square will die off. Similarly, dx by dt will also die off. E raised to minus 2t, because it is minus, that will also die off. So what remains is that 5x is equal to 12 or x is equal to 12 by 5. This is another way of doing the problem, which is an easier version, and you can definitely adopt this. Moving on to the 10th problem. The output of the linear times invariant control system is CT for a certain input RT. If RT is modified by passing it through a block whose transfer function is e raised to minus s. So what does this block do? It will just delay whatever comes to it. Okay, so if CT is coming to it, CT will be delayed by one time unit because it is e raised to minus s. It is a delay because it is e raised to minus s. On the other hand, if it is e raised to s, it can advance it. So e raised to minus s is responsible for delaying CT to CT minus 1. Okay, and of course it is, and that it starts off only at t equal to 1 can be shown by multiplying CT minus 1 by UT minus 1. Okay, and this is exactly what is asked. And then applied to the system, the modified output of the system would be CT minus 1 into UT minus 1. As simple as that. Okay, the last problem. These are better ways of doing such problems rather than taking the Laplace transform and going through the whole procedure. Okay, so the 11th problem tells us that the Laplace transform of ft is fs, given fs is equal to omega s square plus omega square. So what is this Laplace transform of? It is of sin omega t. Okay, because omega by s square plus omega, and sin omega t just continues towards infinity, and you don't have a final value of t equal to infinity because you don't have, it's a periodic function. Okay, the final value of ft is what? None, it's not infinity, it's not 0, it's not 1, it's none of these. Okay, so that's all that's there. So in this problem, in this segment wherein we were discussing time responses, we discussed the response at t equal to 0, at t equal to infinity, for different ways in which the system is expressed, be it in differential form or be it in the Laplace transform form. We also looked at the responsibility of the system to to either build up to a step response or to a decay to the zero value for a step response. Okay, and then we also looked, yeah, so in both contexts, one is a build up, which was when we saw that CT develops to a value equal to 2 over a time, where the initial slope alone is equal to 10. Okay, so we also looked at a situation where 2 into e raised to s 2 by s plus 1 was talking about a decaying, okay, to 0. And then, so we just looked at the percentage component for which the responsibility lay with the exponential quantity. Okay, and we also looked at a system wherein when you apply a impulse, you get a particular response. So if you apply, on the other hand, a step input, what do you get? By just simply by integration. Okay, we saw that any integral controller, okay, coupled or not coupled with a constant and a proportional controller will always see to it that the response is steady and equal to the input. Okay, yeah. So these are some, and then the one particular problem we tried to take the Laplace inverse by just splitting up the numerator into two. That's 1 minus 2s by 1 plus s, so 1 plus s by 1 plus s minus 3s by 1 plus s, and then multiplication by 1 plus s tells us that we can easily do this particular problem by taking the Laplace inverse and finding the values at t equal to 0. So I suppose the next session will also be as simple as this. As was said earlier, control system happens to be much simpler when compared to signal systems, and you can gather a lot of marks in the gate examination context. Thank you.